Have you ever wondered what lies at the darkest corners of our universe? A place where even light cannot escape. A place where time slows down. A place where the laws of physics break down into mystery. Yes, I'm talking about black holes. Do you know that inside our own galaxy, the Milky Way, there is a monster sitting quietly at the center? This monster is millions of times heavier than our sun, and it's a supermassive black hole called Sagittarius A. Today, in this journey, we will dive deep into black holes, what they are, how they are born, their mysteries, their role in shaping the universe, and how modern science is trying to unlock their secrets. In this video, we will explore the mysterious world of black holes, explain step by step, chapter by chapter, so that you can understand every concept clearly and easily. Chapter 1. What is a black hole? In the simplest words, a black hole is a region in space where gravity is so powerful that nothing can escape from it, not even light. This means if you get too close, there is no way out. It's like falling into a cosmic trap from which escape is impossible. But why is the gravity so strong? Because the mass of a star or a huge amount of matter is squeezed into an extremely small space. This results in infinite density at the center, called the singularity. Think of it this way. Imagine you compress the Earth into the size of a small marble. The gravity would be so strong that even light would not escape. That's what a black hole is. Chapter 2. History and Theories. The idea of a black hole is older than you might think. In 1783, an English scientist named John Michell first imagined an object so heavy that even light could not escape. He called it a dark star. Later, in the 20th century, Albert Einstein's general theory of relativity, 1915, gave the mathematical foundation to understand such objects. Soon after, in 1916, a German physicist named Karl Schwarzschild used Einstein's equations to describe a region in space where gravity would be infinite. This was the first exact solution for a black hole. At that time, many scientists thought this was just theory. They didn't believe nature could actually create something so extreme. But today we have evidence. Not only do black holes exist, they are common in the universe. Chapter 3. How are black holes formed? So how does nature make a black hole? The main source is dying stars. Stars are basically nuclear reactors in space. They burn hydrogen into helium, producing energy and light. As long as nuclear fusion continues, the star shines and fights against gravity. But what happens when the fuel runs out? If the star is small like our sun, it becomes a white dwarf. If the star is medium-sized, it becomes a neutron star. If the star is massive, at least 20 times heavier than our sun, then gravity wins. The star collapses under its own weight. The outer layers explode as a supernova, and the core shrinks into a point of infinite density. This is how a stellar black hole is born. Chapter 4. Structure of a black hole. You might be wondering, if black holes are invisible, then how do we even describe them? Scientists divide a black hole into different parts. 1. Singularity, the very center, infinite density. All the mass is concentrated here. The laws of physics break down here. Our equations cannot describe it fully. Event horizon, the boundary around the black hole. It's the point of no return. Once you cross it, escape is impossible. Accretion disk, a glowing ring of hot gas and dust swirling around the black hole. As matter spirals in, it heats up to millions of degrees and shines brightly in X-rays. So while we cannot see the black hole itself, we can detect the accretion disk and the effects it creates. Chapter 5. Types of black holes. Not all black holes are the same. They come in different sizes. 1. Stellar mass black holes formed when massive stars die. Few times to a few dozen times heavier than the sun. Intermediate black holes. Middle size. Hundreds or thousands of times the mass of the sun. Rare and difficult to detect. Supermassive black holes. Millions or even billions of times heavier than the sun. Found at the centers of galaxies, including our Milky Way. Example, Sagittarius, 4 million times the sun's mass. Primordial black holes, theoretical. Tiny black holes formed just after the Big Bang. Still a mystery. No proof yet. Chapter 6. What happens if you fall into a black hole? Here's the most fascinating and terrifying question. What if you fall into a black hole? As you approach, gravity gets stronger. Your feet, closer to the hole, feel more pull than your head. This stretches you into a long, thin shape. Scientists call this spaghettification. To an outside observer, You would appear to move slower and slower, as if frozen at the event horizon. Your light would get redder and fade away. But from your perspective, you would fall in normally, reaching the singularity. Time itself behaves differently near a black hole. This is called time dilation. Closer to the black hole, time runs slower compared to far away. So black holes are not just objects, they are laboratories of space and time itself. Chapter 7. Black Holes and Our Galaxy. Did you know? At the center of almost every galaxy, scientists believe there is a supermassive black hole. In our Milky Way, Sagittarius A, in the Andromeda Galaxy, a black hole 100 million times the mass of the Sun. In giant galaxies, some black holes are billions of solar masses. These monsters play a key role in galaxy evolution. They control star formation, they produce jets of energy, and they shape the structure of galaxies. In fact, without black holes, galaxies might not even exist in their current form. Chapter 8. Quasars, the brightest objects. When a supermassive black hole is actively feeding on gas and dust, it creates an incredibly bright disk called a quasar. Quasars shine so brightly that they can outshine their entire galaxy. They are powered by black holes billions of times heavier than the Sun. Quasars are so far away, yet so bright, that we can see them from billions of light years across the universe. They are basically the cosmic lighthouses of black holes. Chapter 9. Hawking radiation. Do black holes die? Here's a surprising fact. Black holes are not eternal. In 1974, the famous physicist Stephen Hawking proposed that black holes slowly lose energy through a process called Hawking radiation. It means black holes can evaporate very slowly, taking billions or even trillions of years. A tiny black hole might disappear faster, while supermassive ones take longer. This discovery changed everything. It showed that black holes are not just destroyers, they also obey the laws of thermodynamics. Closing of Part 1. So far we have learned what black holes are, their history and origin, how they form from dying stars, their structure and types, what happens if you fall inside, their role in galaxies and quasars, and even that they can die slowly through Hawking radiation. But this is just half the story. The real mysteries are yet to come, like wormholes, parallel universes, black hole information paradox, gravitational waves, and the future of black hole research. Stay tuned, because in the next part, we go even deeper into the unknown. Chapter 10. Wormholes, the cosmic shortcuts. Black holes don't just swallow matter. They may also connect different parts of the universe. The idea is called a wormhole, or Einstein-Rosen bridge. Imagine space and time as a sheet of paper. If you fold the paper, two distant points touch each other. A wormhole would act like a tunnel connecting those points. Some scientists believe black holes might be entrances to such tunnels. If true, wormholes could allow faster than light travel, or even access to other universes. But there's a problem. Wormholes are unstable. They would collapse instantly. To keep them open, we might need exotic matter with negative energy. So, are black holes cosmic portals? We don't know yet, but this is one of the most exciting possibilities in physics. Chapter 11. Time travel and black holes. Black holes don't just warp space, they warp time too. Near a black hole, time slows down compared to far away. This is called time dilation. This concept was beautifully shown in the movie Interstellar, where astronauts near a black hole experience only a few hours while decades pass outside. Is it just science fiction? Actually, no. This is real physics based on Einstein's relativity. But practically, it's extremely difficult to reach such conditions. So black holes are not time machines we can use, but they show us that time itself is flexible, not absolute. Chapter 12. The Information Paradox. Now comes one of the biggest mysteries in science. When something falls into a black hole, say a star, a planet, or even a spaceship, what happens to the information about it? Physics says, information can never be destroyed, but black holes seem to destroy it forever. This contradiction is called the black hole information paradox. Stephen Hawking once suggested that information is lost, but later, theories proposed that maybe information is encoded on the event horizon, like a cosmic hologram. This idea gave birth to the famous holographic principle, that our entire universe may actually be like a 3D hologram projected from a 2D surface. Yes, black holes are forcing us to rethink the very nature of reality. Chapter 13. First picture of a black hole. For decades, black holes were invisible. We could only detect them indirectly, but in April 2019, history was made. The Event Horizon Telescope (EHT) collaboration released the first ever image of a black hole. It was the supermassive black hole at the center of galaxy M87. What we saw was a glowing ring of hot matter surrounding a dark shadow, the event horizon. This image proved black holes are real, not just theory. It was one of the greatest achievements of modern science, involving telescopes across the entire Earth working together. In 2022, scientists did it again, this time imaging Sagittarius A, the black hole at the center of our own Milky Way galaxy. For the first time, humanity has looked directly into the heart of darkness. Chapter 14. Gravitational Waves. The Voice of Black Holes. Another breakthrough came in 2015, when scientists detected gravitational waves for the first time. Gravitational waves are ripples in space-time, predicted by Einstein 100 years earlier. They were detected by the LIGO Observatory. The source? Two black holes merging together. This was mind-blowing. It was as if the universe itself was speaking to us, through vibrations in space-time. Since then, we have detected dozens of such events, black holes colliding billions of light-years away, yet shaking space-time here on Earth. Black holes are not just destroyers. They are also creators of the most powerful waves in the universe. Chapter 15. Black Holes and Future Space Travel. Here's a wild idea. Could black holes help us travel across the universe? Some scientists imagine using the energy from rotating black holes. A spinning black hole has enormous energy that could, in theory, be extracted. Others think that if stable wormholes exist, they could act as shortcuts for interstellar travel. Of course, this is far beyond our current technology. But one day, advanced civilizations might actually use black holes as gateways or power sources. Science fiction today could be science fact tomorrow. Chapter 16. Black Holes and the Fate of the Universe. What role will black holes play in the future of the cosmos? Over billions of years, stars will die out. Galaxies will grow quieter. Only black holes will remain, slowly evaporating through Hawking radiation. In the far, far future, the last whispers of the universe will be the death of black holes. This era is sometimes called the black hole era of the universe. So, in a way, black holes are both the end and the beginning. They are the ultimate survivors. Chapter 17. Black Holes and Human Curiosity. Why do we study black holes? Because they challenge our understanding of reality. They sit at the edge of physics, where general relativity and quantum mechanics collide. To solve black holes, we may need a theory of everything. One theory that unites all forces of nature. This could unlock answers not just about black holes, but about the birth of the universe itself. Black holes are like cosmic teachers, pushing humanity to expand its mind. Conclusion. The darkest mystery. So, what have we learned in this incredible journey? Black holes are regions where gravity is infinite. They form from collapsing stars and exist at the centers of galaxies. They bend space and time, create quasars, and even radiate energy. They might connect universes, hide information, and reveal the holographic nature of reality. We have photographed them and listened to their waves. They may decide the fate of the cosmos itself. And yet, the more we learn, the more mysterious they become. Black holes remind us of our smallness, and at the same time, they remind us of our greatness. Because even though they swallow light, we humans have found a way to shine light upon them. The story of black holes is the story of curiosity, a story that will continue as long as we dare to ask questions. In the heart of darkness lies the key to ultimate knowledge. Black holes are not the end. They might just be the beginning.